Ladies and gentlemen of Algebra 2, we are looking at 5.4, talking about multiplying probabilities, and kind of looking at what happens when you have compound independent and compound dependent events. Basically, if I start combining events together, what are those probabilities going to look like? So that's kind of what we're looking at here. So let's kind of get right into it. Compound is combined events. That's kind of what you're looking at. Two or more events that can happen either at the same time or one directly after the other. So combined independent events. Remember, independent means one has no effect or whether or not the other event happens. Okay, so if I was flipping a coin and rolling a dice, the coin does not affect the dice does not affect the coin, or it's just something similar to that. So they're each independent events. So the probability of A happening and B happening just means I'm going to multiply those two things. Okay, so all I'm doing, multiplying those probabilities together. And like I said, I prefer fraction form. Just to me, it makes the most sense. Decimals get long and ugly and kind of, they just don't look very good. So if I take a look here, Julio reaches into an ice-filled cooler containing 8 regular soft drinks, 5 diet soft drinks, removes a can and decides he's not really thirsty and puts it back. What's the probability that Julio and the next person to reach into the cooler both randomly select a regular soft drink? So you've got 13 total. All right, so there's 8 regular soft drinks. So for Julio, that probability is going to be 8 out of 13. Now, he puts it back, so that it's kind of like the event never happened, okay? There's still 13 in it after he puts it back. So what's the probability that the next person also gets a regular soft drink? Well, that's going to be 8 out of 13 as well. So the probability that they both do is going to be 8 out of 13 times 8 out of 13, which is going to be 64 out of 169. Now, can you simplify that? Not really. So there's my probability. If you really want to put a decimal or get an idea, that's about 38% chance of that happening. So a state lottery game, each of the 3 cages contains 10 balls. The balls are labeled 0 through 9. What's the probability that the first 2 will be even and the third will be prime? So I don't include 0. 0 is not even. Okay, so even is going to be 2, 4, 6, and 8. So that's going to be, so for the first one to be even, that's going to be 4 out of 10. Second one, that's even. That's got 0 through 10 as well, and it doesn't matter what the first one got. What's the probability of just the second one being even? That's going to be 10 as well. And then if I look at the prime would be 1, 2, 3, 4, 5. Oop, not 4, sorry. 7. So 1, 2, 3, 5, and 7. Again, 0 is not prime. And also after double checking, 1 is not going to be prime either. So I've got 2, 3, not 4, 5, 7, not 8, not 9. Boom. So the probability of prime is going to be 4 out of 10 as well. So the probability of all these things happening means I'm multiplying all these things. So a drop down, that's 2/5 times 2/5 times 2/5. So that's going to be 2 times 2 is going to be 8. 5 times 5 times 5 is going to be 125. So that's going to be my probability. And if you want it in a number, in a percentage, that would be so that's going to be 6.4% of that happening. Okay, that's the only time it's going to happen. So all I did was figure out each individual probability and multiply them together. So now compound events are fitted in 2 categories: independent or dependent. Compound events, again, it's 2 events that I'm putting together, and I'm looking at independent, dependent, except for here, compound events, I'm going to add those things. So, independent, dependent, tossing a coin, rolling a die. Like I said before, one has no effect of the other, so that one's going to be independent. Selecting a red apple, then a green apple from a bag of 6 red and 4 greens. If no apples are returned to the bag after being selected. So once I take an apple out, that changes the problem. So that's going to be dependent. So for letter C, we're selecting a red apple, then a green apple from a bag of 6 in red and 4 green. If the first apple is returned before the next one's selected. So this one's going to be independent because once I put it back, it's kind of like the first event never happened. The scenario is still the same and the information is still the same. So that's kind of what I'm looking at there. So probability of dependent events is going to look like this. So I figure out the probability of the first event, and then I figure out the probability of what can happen after that. So find the probability of drawing 3 cards of the same suit from a standard deck of cards without replacement. So if you've got the notes with the deck of cards on it, that might be a handy thing to have in front of you right now. So 3 cards of the same suit. So suit is either hearts, diamonds, spades, or clubs. Probability of drawing 3 cards of the same suit from a standard deck of cards without replacement. So the probability, so if I'm trying to draw all hearts or diamonds or whatever, it's going to look like this. For the first card, it doesn't matter what I draw, so that's going to be 52 out of 52. But for the second card, okay, that means I've chosen a suit, so that means there's 12 suits left. There's 12 cards left out of 51 cards. Then there's 11 out of that suit left out of 50 cards. Now, here's kind of why this is. This is because, you don't know which suit. Okay, you're just drawing a card. Then after you pick the first card, then these two are the ones that have to match. All right, so once you pick a card, that means that is the suit that you're looking for. So then after that, you look at what's left. Well, there's 13 of each suit originally, so then there's 12, then there's 11. So this is like saying 1 times 12 over 51 times 11 over 50. So when I multiply that together, simplify it, I get 22 over 425. If I take that, so if you got about 0.052, that would be the equivalent. So if you want to compare that, that's what you would get. So if I look here, determine if they're independent or dependent, then find the probability of each event. So if I'm looking here, 3 cards are drawn from a standard deck of cards without replacement. Without replacement means dependent, because it says without replacement. Heart, heart, and spade in that order. So out of a standard deck of cards, there are 13 hearts. So that's a probability of the heart first. Then another heart, well, there's 12 hearts left out of 51 cards. And then there's still 13 spades, but there's only 50 cards left. So that's going to be what that looks like. So probability of a heart, 13 out of 52, which is a fancy way of saying 1 out of 4, times 12 out of 51 times 13 out of 50. So multiplying all those, and for goodness sake, let the calculator do most of this legwork for you. So that's going to be 156 over 10,200. So I can simplify that. That's going to simplify to 13 out of 850, which as a decimal, it's 0.0153. So 1.53% of that happening. So that's your probability of that. Now, you spin a spinner numbered 1 to 7 and toss a coin. What's the probability of getting an odd number on the spinner and a tail on the coin? Well, that's going to be independent because the spinner and the coin are 2 different things. Odd number on the spinner, so 1, 3, 5, 7. That's going to be 4 out of 7. And then a tail on the coin is going to be 1/2. All right, so that's just going to be 4 out of 14, which simplifies to 2 over 7. There's my answer. That one wasn't too hard, I hope. So you're reaching into a bag of Scrabble tiles. The bag has 1 tile with each letter. You pull out first 1 tile, then another. What is the probability that you pull out a vowel and a consonant? So you don't put it back, so it's dependent. First 1 tile, then another. You pull out a vowel, then a consonant. Vowel, A, E, I, O, U. I'm not counting Y or W, even though I know sometimes they play that game. So you're going to go 5 out of 26. Then there's still going to be 21 consonants in there, but there's going to be 1 less tile. So it's going to be 5 out of 26 over 5 out of 26 times 21 out of 25, because that's a probability of the vowel, and that's a probability of the consonant. So that's going to be 5 divided by 26 times 21 divided by 25. So that simplified becomes 21 out of 130. Convert to decimal, 0.1615, or approximately 16.15%. That's what that answer is going to look like. Card is chosen at random from a deck of 52 playing cards without replacing it. Here is my big key term there. A second card is chosen. What's probably the first card is a queen, second card is a jack. Well, it's going to be dependent because I'm not putting it back. So that's my replay. So that's how I know it's dependent. So first card's a queen. Well, there's only 4 queens out of the deck. So it's 4 out of 52. Then a jack. There's only 4 jacks, but once I take a card out, there's 1 card less. So that's just going to be 4 out of 52, which is another way of saying 1 out of 13. So that's going to be 4 out of 663. So 4 divided by 663 as a decimal is 0.006. So even as a percentage, that would be 0.6%. Very, very rare to do that. All right, last one. 4 cards from a deck of 52 playing cards with replacement. 4 hearts in a row. So you're almost to a flush. If you got 5 hearts, that'd be a flush. But here is your choosing 4 hearts in a row with replacement. So you put it back each time. So that's going to be independent. So that's going to be 13 out of 52 times 13 out of 52, because you're putting it back each time. So another way to think about that would be 13 out of 52 raised to the 4th. So 13 out of 52 is another way of saying 1/4 raised to the 4th. So the probability of doing that is going to be 1 out of 256. That's going to be my probability. So that's going to be 0.0039 as a decimal. All right, play around with this, look at this. Be very, very picky, read over problems. Look for clues like with or without replacement to kind of tell you if you're independent or dependent, compound, or what you are. If you have any questions, come talk to me. Otherwise, have a good one.